roughly 311 miles, about 500 kilometers west of Oregon's shoreline, far below the gray swells of the Pacific. A hidden volcano rises from the abyssal plain. This undersea mountain, called Axial Seamount, sits squarely along the fiery backbone of the Pacific Ring of Fire, the vast horseshoe of faults and volcanoes that girdles the ocean. The Pacific Northwest is no stranger to restless geology. It is home to the Cascades and to infamous peaks like Mount St. Helens, whose 1980 blast still serves as a cautionary tale. The story stretches back millions of years to when the Pacific Plate began diving beneath North America. That slow-motion collision helped build the Cascade Arc from Northern California into British Columbia, and it also set the stage for submarine giants like Axial. From the seafloor, it climbs like a dark cathedral, its summit still roughly 5,249 feet, about 1,600 meters, beneath the sea surface. Lately, something unusual has been stirring down there. In a single day, instruments recorded more than 300 earthquakes around Axial, a spasm of motion that is far from routine. The pattern of shaking has scientists on high alert because it resembles the run-up to the seamount's previous eruptive episodes. One veteran oceanographer put the risk in stark terms. If this were happening beneath a town rather than beneath thousands of feet of water, emergency managers would already be clearing neighborhoods and putting evacuation plans into motion. The Pacific may look calm from a ferry deck. The forces below are anything but. So what's driving this drumbeat of quakes? The best explanation points to magma creeping upward through fractures in the oceanic crust. As molten rock pushes into the plumbing system beneath the summit, it pressurizes the volcanic edifice. Think of a balloon being slowly inflated inside a rigid box. At some point, the pressure has to find release. When that moment comes, the seafloor can split, lava can pour out, and the volcano can undergo an eruption, measured not in towering ash plumes, but in rivers of basalt that harden into black glass on contact with cold seawater. The year 2025 has already delivered several eyebrow-raising bursts of activity. In June, instruments tallied an astonishing flurry, more than 2,000 earthquakes in just 24 hours. That spike eventually eased, settling back to roughly 100 tremors per day for a time, but counts have again climbed into the hundreds. Even without any one massive jolt, the sheer persistence of these tiny quakes is a red flag. To grasp the scale, remember what happened the last time Axial really let loose. During the April 2015 event, over 8,000 earthquakes were logged in a single day. That is the tempo of a volcano in full swing. Today's numbers are lower, but the trend line and the style of the signals echo that run-up. And that is why researchers are treating the present sequence as more than a curiosity. A second, equally troubling clue is showing up in the shape of the volcano itself. Axial appears to be inflating, its surface subtly lifting as new magma collects in a reservoir beneath the summit. Before the 2015 eruption, that ballooning reached a notable threshold, and measurements now suggest the edifice has swelled back to similar levels. The tempo of uplift has accelerated too. Whereas typical years saw the ground rise on the order of 2 to 4 inches, roughly 5 to 10 centimeters, the rate jumped dramatically beginning in January 2024. By July, some stations near the center of the caldera had captured as much as 6 inches, about 15 centimeters, of cumulative uplift, and peak pockets were pushing toward 10 inches, around 25 centimeters. That's a remarkable amount of motion for rock to undergo in such a short interval, and it fits uncomfortably well with the surge in microquakes. Both are classic symptoms of a magmatic system under pressure. All of this is unfolding inside a volcano with serious dimensions. Axial is not a neat cone. It's a sprawling complex capped by a caldera and rift zones that stretch for miles along the seafloor. The main magma storage zone sits around 2,625 feet, about 800 meters, beneath the top of the edifice, a sizable chamber of molten rock feeding the system. Although its summit remains more than 1,000 meters below the ocean's surface, which muffles direct effects on coastal communities, there is nothing small about the forces at work. For volcanologists, Axial is both a laboratory and a test. Here's a system we can watch closely, one that erupts often enough to study modern processes in real time, and one that can teach us about the rhythms of more dangerous volcanoes on land. Predicting eruptions is notoriously difficult, but Axial may be giving scientists the best shot yet at a well-timed forecast. The volcano has a quirky personality. Periods of rapid inflation can be followed by quiet plateaus, then by renewed surges. But the current combination of inflation, seismicity, and the sheer pace of change has led some researchers to a striking conclusion. Odds favor an eruption before the end of 2025, possibly at any time. That doesn't mean a cataclysm is guaranteed, and the ocean will absorb much of the spectacle. Yet from a scientific standpoint, capturing such an event with modern eyes could be historic. That's because the monitoring toolkit on site is far better now than in previous cycles. A sophisticated network of cables, junction boxes, and sensors sits on and around the caldera, streaming data continuously. Tilt meters watch the ground breathe. Pressure gauges register tiny changes in the overlying water column. Seismometers listen for the crackle of moving magma and the pop of breaking rock. Some nodes are tied into cameras and chemical sensors, ready to catch visual signs, plumes of shimmering water, sudden turbidity, or hydrothermal fluid bursts, should the seafloor split. Instead of occasional research cruises, stitching together snapshots weeks or months apart, scientists now have a live feed from the deep, second by second. If Axial opens a new fissure, that system could record the sequence with a level of detail never achieved for a submarine eruption. The earthquakes being tallied are not large in the way the public imagines earthquakes. Most cluster around magnitude 1 to 2. But in a volcanic setting, that's exactly what you'd expect. Swarms of small events that collectively map the path of magma as it wedges itself into cracks. Each tiny quake is a stress whisper, a brittle fracture here, a slip there, a local pressure drop, followed by renewed push. The pattern matters more than any single number. A broadening swarm, increasing rates, a change in the dominant depths. These are the signatures forecasters watch, and recently those signatures have been trending in the direction of unrest. It's worth emphasizing that undersea eruptions differ profoundly from those on land. There will be no ash cloud blotting out the sun, no red fountain visible from coastal highways. The pressure of 1,000 meters of seawater forces lava to quench instantly into jagged pillow shapes, piling up like toothpaste squeezed into ice water. Still, the consequences can be significant. New lava can dam or reroute hydrothermal circulation, altering ecosystems. Seafloor topography can change over days. In some cases, gas release or rapid heating can drive local hazards at the surface, though at Axial's depth, the ocean generally dampens such effects. For ships and nearby infrastructure, the main risks would be to sub-sea floor cables and instruments, not to ports and cities. Even so, studying Axial is not an academic luxury. The physics of magma moving through rock are universal. Lessons learned here: inflation thresholds, the relationship between seismic swarms and dike intrusions, the way pressure migrates through a branching rift network, translate to stratovolcanoes that do loom over towns and highways. Every data point from Axial sharpens our playbook for hazards on land. If researchers can validate a reliable chain of precursors at this seamount and peg the timing of an eruption within a meaningful window, it would represent a milestone for eruption forecasting writ large. None of this erases the reality that volcanoes can faint. Axial's history includes stretches of rapid uplift that stall, intervals where quakes scatter then regroup, and episodes where magma intrudes along a rift without breaking the surface. Forecasts must dance with uncertainty, but uncertainty is not ignorance, and it is not paralysis. It is a quantified range, narrowed by each new sensor, each fresh data set, each additional hour of continuous monitoring. Right now, the picture looks like this. The volcano has reinflated to levels comparable to those seen before the 2015 eruption. The rate of inflation accelerated markedly, beginning in early 2024. Earthquake counts surged to extraordinary highs in June 2025 and continue at elevated levels measured in the hundreds per day, and the overall behavior suggests a pressurized system. The simplest interpretation is that magma is on the move and that the system is trending toward a release. If and when that release happens, the sequence is likely to unfold rapidly. A dike, a blade-like body of magma, could propagate along one of Axial's rift zones, opening a fissure on the seafloor. Seismicity would spike, then reorganize into a migrating front as the intrusion advances. Tilt meters might register sudden steps. Pressure sensors could show subtle changes as warm fluids pulse outward. Cameras, if lucky enough to be pointed in the right direction, might catch the water clouding and shimmering. Lava would extrude and cool into lobate pillows, building new crust, even as the underlying reservoir deflates and the ground above sags. After days to weeks, the system would quiet, leaving behind a freshly minted patch of ocean floor and a trove of measurements for scientists to decode. For now, the best course is vigilance. The deep ocean network continues to hum, logging every tremor, every millimeter of rise or fall. Research vessels stand ready to sail when weather windows open. To ground truth, the signals with plume sampling and high-resolution mapping. And the public, though insulated by distance and depth, can take real comfort in the fact that this is a volcano we can watch in detail, one whose behavior is teaching us how to read the signs at other, more immediately consequential volcanoes around the world. Curiosity about Earth's hidden machinery is more than a hobby. It's a form of preparedness. The more we understand how magma moves, how rock responds, and how seafloor systems breathe, the better we can anticipate the next chapter, underwater at Axial, or atop a mountain closer to home. If this kind of deep time detective work fascinates you, stay tuned. We'll keep translating the pulses of the planet into stories you can see and understand, as this undersea giant writes its next line in the Pacific's long volcanic script. During the Second World War, the island now officially called Ioto, known to many from that era as Iwo Jima, was a name etched into history. Today, this small volcanic outpost in the Pacific, situated roughly 1,200 kilometers, about 746 miles, south of Tokyo, is writing a different chapter. The ground has stirred yet again, and with it, a new threat has risen from below. An eruption style born not only of molten rock, but of scalding water and explosive steam that can remodel the island in a matter of minutes. At the island's southern end, Mount Suribachi, a low, brooding stratovolcano that once provided a strategic vantage point and the iconic scene of a flag raising, has become the backdrop to a fresh sequence of volcanic unrest. Ioto is not merely a battlefield relic. It is one of the most active volcanic environments in Japan. The island perches along the Izu-Bonin-Mariana Arc, a chain of submarine and emergent volcanoes that trace the subduction of the Pacific Plate. For generations, residents and station personnel lived with the nuisances of a breathing volcano. Subtle quakes, fetid fumaroles, hot soils that steamed after rain, and sulfur in the air. Recently, however, the tempo and texture of the activity have changed, pointing to a system rebuilding pressure, reorganizing pathways, and testing the limits of the rock that contains it. Just after dawn on September 2nd, a thunderous detonation broke the morning calm and echoed across the water. What might have been dismissed as a single burst revealed itself as a complex, multi-stage event. Instead of a solitary vent, 5 separate craters opened in a short span. Each crater told its own story about where pressure was highest, where fluids could escape, and which fractures had been pried open by rising heat. The culprit was not a true magmatic fountain at the surface, but a different, notoriously unpredictable style of eruption. Phreatic blasts. In these events, hot magma at depth doesn't necessarily erupt, but it flashes shallow groundwater to steam. That water, in an instant, expands by a factor of more than 1,000, turning the subsurface into a boiler under extreme stress. If confining rocks fracture, The trapped steam tears upward, blasting out old sediments, ash, altered rock, and occasionally hot fragments ripped from magma that never quite made it to daylight. The 5 craters did not scatter randomly like buckshot. They aligned along pre-existing zones of weakness, geological seams etched into the island over many thousands of years. 3 erupted in near unison, as though triggered by the same pressure pulse, traveling up a hidden conduit network. 2 others tracked along a mapped fault, locally referenced as the Akiji/Asidi structure, revealing that much of the island's plumbing is governed by old breaks in the rock. Volcanic systems frequently exploit these weaknesses. Once a crack opens, it becomes the preferred path for fluids and heat, the way a river returns to its channel after a flood. Dimensions alone convey the violence of the blast sequence. The smallest crater measured on the order of 35 meters, about 115 feet across, while the largest yawned opened to nearly 150 meters, close to 492 feet in diameter, a span that could swallow a football field with room to spare. Carving cavities like this requires an astonishing release of energy, comparable to detonating large stores of explosives underground. And yet the most striking detail may be what some of the craters threw out. Not only shattered clay, sand, and hydrothermally altered rock, but also incandescent bits of lava. Those glowing fragments imply magma lay very shallow, perhaps only a few tens of meters beneath the surface, close enough for the blast to rip pieces from its skin. Observers reported, or in some cases inferred from deposits, brief low run-out pyroclastic surges, hot turbulent clouds of ash and gas that skim along the ground at racing speeds. These were limited in extent, but their possible presence elevates the hazard profile beyond a simple steam burst, suggesting a complex interplay of heat, gas, and fragmented material. By the end of the episode, roughly 192,000 square meters, about 474,000 square feet, of terrain had been dusted and draped with new tephra. The island's map shifted yet again. Perhaps the most dramatic change was literal accretion of land. At the westernmost crater, so much debris was heaped outward that the shoreline advanced. Approximately 25,100 square meters, around 270,000 square feet of fresh surface, was added to the island's margin. On Ioto, growth is not a metaphor. It is a measurable expansion of real estate driven by eruptive power and sediment redistribution. A reminder that Earth's skin is perpetually under construction. For scientists, the craters are only the surface signature of a deeper process. A key diagnostic of that process is geodetic uplift, the island physically rising as magma and hydrothermal fluids pressurize the system below. During the first days of this sequence, precise instruments captured the ground lifting by about 10 centimeters, roughly 4 inches, per day. In the slow language of geology, that is a shout. Such rapid vertical motion implies substantial magma input or redistribution in shallow reservoirs. To make room for rising melt and superheated fluids, the brittle crust domes up like the lid of a pot under boil. Then a shift. The uplift pace slowed markedly. First, daily rise dropped by half. Then it halved again. Eventually, it settled near 0.5 centimeters, about 0.2 of an inch per day. To the casual reader, that might sound reassuring, a sign that the crisis has passed. Specialists are more cautious. A decline in uplift can mean depressurization after an eruption, but it can also indicate that fluids found new pathways, or that magma migrated laterally into a different pocket, or that gases are venting more efficiently through the newly opened fractures. In other words, the pressure did not necessarily vanish. It may have simply moved. From September 1st onward, cumulative uplift reached roughly 24 centimeters, about 9.4 inches, adding to years of steady rise. The long view is even more striking. The shoreline set during World War II now stands about 20 meters, around 66 feet, above present sea level. The beaches where soldiers once waded ashore are today perched high and dry, the ocean's old edge fossilized in terraces that step inland. This is the signature of a resurgent caldera system, a broad, subtle uplift caused by magma repeatedly refilling a large, shallow chamber and by hydrothermal fluids pressurizing overlying rock. Ioto is, in effect, the lid of a massive pressure cooker, and the cooker has been turned up for decades. Since around 2021, the island's restlessness has intensified. Minor eruptions and vigorous degassing have occurred with increasing frequency, each event a symptom of a deep engine that refuses to settle. Although the Volcanic Explosivity Index, VEI rating, assigned to the September episode is a modest one on a scale that tops out at 8, context matters. For this island in the 21st century, it is the largest event of its kind. Magnitude is not just about tall, incandescent fountains. It is also about how much the ground is rearranged, how rapidly the uplift accumulates, and how profoundly the subsurface plumbing is reconfigured. The operational consequences were immediate. Japan's self-defense forces postponed planned aircraft landing drills on Ioto and moved them to another site, an acknowledgement that even short run-out ash surges, ballistic ejections, or sudden ground deformation could endanger crews and equipment. Such decisions are never taken lightly. They reflect risk assessments that weigh the island's volatile temperament against the demands of training and logistics. Why are phreatic eruptions so unnerving? Unlike the classic lava-fed spectacle, they offer little warning. There may be subtle thermal changes, faint seismic tremor, or tiny bursts of gas composition shifts, but the trigger point can be abrupt. A blocked vent clears, a fracture tips open, groundwater flashes to steam, and an explosion follows. Depending on the geometry of the system and the permeability of the rocks, this can happen with minimal precursors that would be obvious to non-specialists. The resulting hazards include violent jets of rocks and ash, ballistics, short, fast-moving surges, and sudden collapse pits where overlying material has been evacuated. On a small island with critical infrastructure, any one of these can compel a rapid change of plans. The 5 new craters also provide scientists with a rare window into the volcano's inner pathways. Their positions and orientations illuminate the stress field, the directions in which rocks are being pulled apart or squeezed, and they reveal how pressurized fluids navigate the subsurface maze. The alignment along 2 principal trends points to an island-scale architecture. One set of fractures, likely tied to regional tectonics. The other controlled by the caldera's own geometry. When future episodes occur, these same alignments may reactivate as fractured rock is easier to reopen than intact rock. Ejecta from the blasts, examined quickly in the field, included lava fragments tentatively identified as trachyte, a silica-rich composition that often forms when magma lingers in the crust, differentiating and evolving chemically. If confirmed, that would suggest a complex and potentially viscous magma system beneath the island, prone to trapping gases and developing overpressure. In such systems, the coupling between the magmatic and hydrothermal realms can be tight. Pulses of heat and volatiles from below can supercharge the steam-dominated layers above, priming them for phreatic bursts, even if the magma itself never breaches the surface. For now, the island continues to breathe. Small quakes tick by, fumaroles hiss, and the ground swells at a slower but still noteworthy pace. Whether the September sequence marks the crest of a cycle or the opening movement of a longer campaign is not yet clear. Both scenarios are plausible. Many caldera systems operate in pulses, with uplift accelerating, eruptive symptoms flaring, and then a tapering phase as the plumbing rearranges. Others ratchet forward in steps, each event creating new cracks and conduits that shorten the path from heat to water, thereby raising the odds of repeat blasts. What is unambiguous is the scale of change, already etched into the landscape. Craters dozens to hundreds of meters wide, a fresh apron of ash and debris, a measurable gain in land area, and a continuing elevation signal that leaves old coastlines stranded far inland. These are the footprints of a dynamic volcano. For those who study risk, The island presents a compact laboratory. Aviation operations, military logistics, and scientific fieldwork all must adapt to a terrain that can reconfigure itself between one survey and the next. Kyoto's story is not simply about explosions, it is about balance. As magma rises, it must find room. As steam seeks escape, it seeks the path of least resistance. When those paths are clogged, pressure builds. When they open, pressure falls, sometimes catastrophically. The 5-crater eruption sequence captured that dance in miniature. A pressurized system sought outlets along familiar faults and newly weakened rock, bled off some of its energy in violent fashion, and in the process modified the very channels that will govern whatever comes next. The practical takeaway is caution without complacency. A falling uplift rate does not mean the hazard has ended. It means the system has changed state. New fractures may now be venting gas more efficiently. Alternatively, magma may have moved laterally, charging another section of the caldera's roof. Monitoring must stay continuous and multi-pronged. High-precision GPS and tilt meters to track surface motion. Seismic arrays to listen for fluid movement and fracturing. Gas sensors to catch shifts in sulfur dioxide or carbon dioxide that hint at magmatic pulses. And remote sensing to map thermal anomalies or shoreline changes after each event. For an island that once symbolized a pivotal human struggle, the present saga is a reminder that the deeper contest between heat from Earth's interior and the brittle shell that covers it never ends. Kyoto has risen meters in a lifetime, carved new pits in an hour, and pushed out its shoreline in a single storm of ash and rock. Whether the next chapter brings more steam-driven violence, a lull, or a different style of eruption altogether, the island will keep telling its story in uplift lines, in crack patterns, and in the grain of fresh tephra that settles on its flanks. And for those watching, the lesson is the same as ever. The ground beneath us is not a static platform, but a living system, sometimes whispering, sometimes roaring, and always reshaping the world we think we know. Sicily's towering fire mountain looms over the island's east like a restless cathedral. Mount Etna, in southern Italy, is not only large by European standards, it is the continent's most energetic volcano, a place where the crust moves and sometimes roars. Its summit stands near 10,825 feet, about 3,300 meters, though the exact number shifts with each outburst as craters build and collapse. For centuries, Etna has cycled through eruptions and pauses, becoming both a research site and a major attraction. That appeal comes with a sober reality. Beauty and danger share the same slope. Etna's behavior does not follow one simple script. It moves along a spectrum, from modest strombolian pops and ash puffs to short, intense episodes that fling columns of molten rock skyward. In the latest chapter, fresh lava has again threaded down the flanks, cutting glowing rivers through black scoria, while orange fountains light the night. Authorities tightened access, keeping people below roughly 8,200 feet, about 2,500 meters, while instruments flagged elevated shaking. The goal is straightforward: admire the show, but keep distance while the mountain's pulse is high. A new feature has become the focal point of concern, a visible fissure on the upper slope. Drone surveys and handheld footage make the crack unmistakable. This is not a surface blemish. Fractures like this reflect underground stress as pressurized magma pries rock apart. Such openings can precede larger events, lateral eruptions lower on the cone, or, in more severe cases, structural slumps that peel away portions of the flank. Scientists have long measured a slow, persistent slide of parts of Etna seaward, a creep that usually proceeds at a walking pace each year, but hints at the forces at work inside the edifice. In rare cases elsewhere, sudden volcanic slope failures have even kicked up waves. That is not a forecast for Sicily, but it explains why a new crack instantly raises the stakes for monitoring. Even as lava fountains and glowing streams seize the eye, the volcano's internal heartbeat, the tremor signal, continues. It strengthens and dips, but together with surface deformation, it points to a system under pressure. Volcanologists are asking a simple question with complicated implications. Is this a familiar pulse in Etna's rhythm, or the start of a deeper reshaping of the mountain's plumbing and flanks? The fracture sits just below the summit crater complex in what specialists call a subterminal zone, near the 3,000-meter contour. That belt is notorious among Etna watchers because stress can accumulate there until the volcano chooses a side vent instead of the summit. Flank eruptions are disruptive. They can open abruptly, cross trails and roads, and send lava toward valleys long unused to flows. Their unpredictability raises risk for hikers, workers, and nearby communities alike. Ground sensors show deformation consistent with magma intrusion, hot material wedging into cracks and lifting the surface. Bi-amount satellites detect even when people notice nothing. The new fissure is likely the surface expression of that push. If intrusion continues, modest activity can escalate into stronger paroxysms, or if rock fails, into local collapses. Recent aerial passes mapped several small vents feeding multiple lava tongues. As they descended, the flows split and rejoined like braids in a river. The farthest fronts reached about 7,546 feet, around 2,300 meters. Higher up, the summit vents above, roughly 9,843 feet, near 3,000 meters, continued to supply fresh magma, turning the upper slopes into a moving assembly line of incandescent rock. In parallel, Italian civil protection raised the alert posture. An F1 advisory signals heightened caution and keeps the summit effectively off-limits. Should conditions escalate to an F2 stance, as happened earlier this season, authorities would warn about fast-moving hot clouds and sudden hazards. A recent dip in seismic chatter may look like relief, but lulls on Etna often precede bursts. Paroxysmal episodes, sudden violent releases of pressure, can drive sky-high lava jets, loft-tall ash plumes, and blast glowing clasts across wide arcs. Those clasts, called lapilli and volcanic bombs, can be as small as gravel or as large as a football, and they travel fast. On busy volcanoes worldwide, people have been injured by projectiles and ash clouds that outran expectations. A grim lesson from New Zealand's Wakari/White Island is that a volcano in routine activity can still switch gears without much warning. Etna is more active than most, so that lesson applies doubly here. Part of the management challenge is Etna's shape-shifting tempo. A cycle can start with tame spattering, leap into fountains, toss short-lived pyroclastic surges, then fall back to a simmer. The newly mapped fracture could mark a deviation from that familiar arc, hinting that structural stress is accumulating in a way that increases the odds of a lateral opening. Italy's National Institute of Geophysics and Volcanology reports ongoing strombolian bursts at the summit with intermittent ash visible from surrounding towns. Analysts watch more than camera images. They track the precise height of advancing lava fronts, monitor the rise and fall of harmonic tremor, and listen for infrasound signatures that reveal explosions even when weather hides the vents. Together, those metrics show magma still moving underground and feeding the surface. Because the system is unsettled, caution is wise. No one can say with confidence how the next day or two will unfold, and that uncertainty is itself a warning sign. Persistent tremor, active deformation, a fresh fissure, and multiple lava sources argue for restraint on the mountain and vigilance in the communities below. A new vent can open with little notice. An existing vent can choke and then clear with more force. Wind can swing an ash plume over a road that was clear an hour earlier. Sicilians have lived with that reality for generations. Ash on the windshield at breakfast and a faint glow on the horizon after sunset are part of the local rhythm. When instruments show rising risk, authorities close trails and restrict access. The latest fracture, together with pressure signals, argues for a stretch of heightened respect. Being prepared, knowing routes, keeping masks, having a communication plan is not alarmist. It is responsible. Round-the-clock monitoring continues. Networks of seismometers listen for swarms, too small for people to feel. GPS receivers and tilt meters register millimeter-scale motions of the ground. Thermal cameras chart the heat of flows and vents. Gas sensors measure sulfur dioxide and other emissions that rise when new magma nears the surface. Drones supply overhead views that ground teams cannot get safely. Together, these tools give a near real-time portrait of Etna's mood and help officials adjust closures and guidance. The broader scientific community follows closely because each Etna cycle teaches lessons that travel. Comparing data from Sicily with other regions sharpens models of magma ascent flank stability, and the thresholds that tip a photogenic eruption into a hazardous one. In that sense, every measurement taken on Etna contributes to the global understanding of how our planet moves heat and material from its depths to the surface. For visitors and locals, the advice remains simple. Enjoy the spectacle from safe lookouts and respect guidance from the park and civil protection. Keep clear of summit zones. While the alert is elevated, the mountain's beauty is real, and so is its unpredictability. Respecting both is how you witness the show, without becoming part of the response. If you're passionate about geology and want more updates as this sequence evolves, stay tuned. We'll keep translating measurements and field notes into plain language. Share your thoughts below. Do you think this fissure signals a larger shift, or will Etna settle back into its familiar cadence? Your perspective helps guide what we explain next, and your caution helps keep everyone safe on the slopes. Quick glossary. Strombolian means rhythmic bursts from gas bubbles at the vent, spectacular but typically limited in range. A paroxysm is a short, powerful peak that can hurl lava high and spread ash widely. Pyroclastic flows are fast, ground-hugging clouds of hot gas, ash, and rock. Rare on Etna, but dangerous enough to drive higher alerts. Lapilli are small cinders. Volcanic bombs are larger blobs that harden in flight. Terms like these explain why rules can change quickly. Last point, volcano science is probabilistic, not prophetic. Analysts merge many weak signals, small gas shifts, subtle tremor, centimeters of tilt, into a picture of rising or falling risk, then revise it as new data arrive. Patience with restrictions and respect for the mountain make safer outcomes possible. Stay informed, stay flexible, and give Etna space. It's starting to feel like mountains everywhere are loosening at the seams. If you've been tracking the recent run of rockfalls and slope failures, you're not alone. Share your take below on what this means for mountain belts and their valleys worldwide. Let's focus on one case study, Hawk Vogel, rising to roughly 8,500 feet, 2,592 meters. It stands apart in the eastern Algae Alps on the Bavaria-Tyrol line, a solitary summit that dominates lower neighbors. Long before official records caught up in 1818, local shepherds were already on its ridges. Surveyors later used the peak as a triangulation point during early mapping efforts, proof of how prominent and reliable a landmark it once seemed. That appearance of permanence hides a touchy geology. Hawk Vogel is built mostly of Maine dolomite, a Triassic-age sedimentary rock. It's tough on the whole, but under the right stress, water, and temperature conditions, it can fracture and fail. History bears that out. On May 27, 1935, a massive failure ripped from the southwest face, sending thousands of cubic yards, thousands of cubic meters of rock downslope. More modest slips followed in 2005, 2007, and 2016. In other words, instability here isn't new. What's changed is the pace and scale of warning signs. The headline issued today is a summit-spanning crack that has been widening and deepening. Earlier measurements described a fissure about 130 feet, 40 meters long, approximately 10 feet, 3 meters wide, and approximately 26 feet, 8 meters deep. By 2024, high-resolution monitoring indicated dimensions on the order of 115 feet, 35 meters, in length, nearly 20 feet, 6 meters across, and roughly 20 feet, 6 meters deep. If a major section lets go, estimates suggest as much as approximately 340,000 cubic yards, approximately 260,000 cubic meters of rock could detach. Enough volume to reshape a valley floor and strip trails, alpine meadows, and infrastructure in its path. Since 2014, geoscientists and engineers, principally from the Technical University of Munich and the GFZ Research Center in Potsdam, have run an advanced warning network known as AlpSense Bench. Think of it as a digital nervous system for the mountain. Laser scanners, geophones, crack meters, GPS, and a continually updated 3D twin-track tiny movements down to hundredths of an inch, tenths of a millimeter. The system's goal isn't fortune-telling, it's pattern recognition. When motion accelerates in ways that typically precede failure, the instruments can flag danger a couple of days in advance. Like a weather forecast, it can detect trends and tipping behavior, but it cannot name the exact hour a block will break. Despite the warnings, curiosity draws people in. Hikers still edge toward the open fracture to see the problem up close. That uneasy mix, spectacle and risk, has turned Hochvogel from an icon of alpine beauty into a live hazard zone and one of the most closely watched mountains in the range. Seasonal conditions amplify the threat. As European summers warm, accelerated snowmelt and heavier rain load the rock mass with water. Rain infiltrates joints and bedding planes, acting like a lubricant, while also adding weight. Over the past 5 years, the crack's width has grown by about a foot, approximately 30 centimeters. A small number on paper, but alarming at this scale. The situation echoes a Swiss case near Blatten, where a slope's movement rate jumped from approximately 0.5 inch per day to approximately 0.5 inch per hour, an escalation that made collapse imminent. That is exactly the kind of acceleration the sensors here are tuned to catch. If a major release occurs, modeling suggests debris could surge into Austria's Hornbach Valley near the Germany border. Population in the direct path is sparse, but there are well-used trails, huts, and grazing areas. The consequences for those sites could be severe, even if towns farther away remain out of reach. To manage that risk, authorities have tightened early warning procedures so that rescue teams, alpine clubs, and local administrations on both sides of the frontier receive immediate alerts. With even 2 days' notice, priority areas could be cleared to prevent casualties. One event may not be the end of it. Specialists expect a stepwise breakdown as possible. Phases of failure spread over months or years. That kind of drawn-out destabilization would keep access limited and require continuous monitoring, with ripple effects for tourism and the local economy tied to mountaineering and hut networks. There's also the human layer. For communities that have lived with the mountain as a backdrop, a place of quiet and challenge, the present uncertainty carries a psychological toll. Trails that once felt routine now demand vigilance. The landscape itself feels provisional. Zooming out, Hochvogel's behavior fits a pattern seen across the Alps. In recent decades, extreme weather has become more frequent. Intense rain, hotter summers, and volatile storms. Lightning is under investigation too. Repeated electrical strikes can micro-damage rock, and when you combine that with prolonged saturation from rain, the structural integrity of fractured dolomite can degrade over time. It's death by 1,000 cuts. No single factor explains it, but together they tip the balance. Monitoring continues around the clock. Millimeters matter here. A slight jump in displacement speed can separate stable enough for now from failure in progress. And the hazard isn't only rockfall. Should a large collapse occur, secondary debris or mud flows could mobilize later, potentially traveling into the Hinterbach Valley and creating follow-on dangers. That's why planners are already sketching longer-term protections, not just emergency responses. Add it all up, climate trends, the natural fatigue of an old mountain, human exposure, and the slow arithmetic of geology. And Hochvogel has become a working laboratory. It's no longer just a summit to photograph or bag. It's a case study in how fast solid ground can change. The old cliché, solid as a rock, doesn't land the way it used to when the rock is riddled with widening joints and measurable motion. What does feel solid is the need to respect both the landscape and the science watching over it. If stories like this catch your interest, stick around, subscribe, tap the bell so you don't miss new deep dives, and pass this along to friends who follow natural hazards. And tell us in the comments what you make of the Hochvogel situation, or if you've seen similar slope instabilities on your own travels. Your experiences help widen the discussion. For those who want a little more technical context, consider the mechanics at play. Main dolomite typically features bedding parallel weaknesses and vertical fractures formed over geologic time. Freeze-thaw cycles widen those voids as water expands into ice, and in warmer seasons, infiltrating rain reduces friction along those same planes. Add the occasional seismic vibration, regional earthquakes, or even distant tremors can contribute. And you have a system primed for episodic movement. Each episode need not be catastrophic on its own, but cumulatively, they can reduce the safety margin until a nudge, an intense storm, a temperature swing, or a saturated week pushes the mass beyond its threshold. That is where monitoring earns its reputation. Laser scanners map the face repeatedly, comparing point clouds to detect subtle bulges or overhang growth. Geophones listen for microcracking, tiny acoustic emissions that hint at bonds failing within the rock mass. Crack meters measure aperture changes across the fissure, while GPS monuments track surface displacement. Feed all that into a living 3D model, and you can see which blocks are moving coherently and which are locked, giving responders a target for closures and evacuations that is grounded in data rather than guesswork. The goal is not to eliminate risk, no one can, but to convert uncertainty into informed decisions that save time and lives. The social piece matters too. Messaging must balance clarity and proportion, neither downplay nor sensationalize. Local guides, HUD operators, and municipal leaders succeed when communications are simple, timely, and consistent. Close today signs need clear detours. Alert levels should be color-coded and explained. Evacuation drills should be practiced in shoulder seasons when routes are less crowded. Small choices like multilingual notices or QR codes linking to live dashboards can save minutes when minutes matter, and visitors can help by treating closures as lines not to be crossed rather than challenges to brag about online. Finally, remember that mountains change on human timescales more often than we think. The Alps are not static museum pieces. They're dynamic landforms shaped by uplift, weathering, ice, water, and gravity. Hochvogel is a reminder that beauty and hazard live side by side. Respect the forecasts, heed the ropes, and treat that widening crack not as a spectacle, but as a message from the rock itself. As we wrap up, a quick note on personal responsibility. If you visit this area, plan conservatively. Check current closures, register your route when required. Carry a map and headlamp even on fair weather days, and turn around early if the ground or the forecast feels wrong. The summit will be there tomorrow. Your margin for error may not.